All right, in this we're going to look at another couple examples of the Peel method. And you can see I put some trig identities up here, kind of the important one we're going to need. And we're going to look at two situations to begin with. If there are even powers and if there are odd powers. Well, if there are even powers in both, okay, tangent of x to the eighth, secant of x to the sixth, knowing that the derivative is tangent, okay, I'm going to start, knowing the derivative of tangent, I'm going to think that if I made u tangent, then du is secant squared. So here's what I'm going to do. I'm going to peel off a secant squared. So I'm going to have tangent eighth of x times secant to the fourth times secant squared. And then I'm going to use this up here. I'm going to say, well, tangent squared plus 1 is secant squared, so I should be able to rewrite this as tangent squared plus 1 squared. So tangent to the eighth, 1 plus tangent squared times secant squared. And now I can use this substitution right in here. And my integral becomes u to the eighth times 1 plus u squared du. And, of course, to do this, you would actually multiply it out, 1 plus 2u squared plus u to the fourth. You'd multiply this in, I'm going to run out of room, multiply it in, and then do power rule. In the interest of space and time, I'm going to stop there. But the important thing here is to realize that we can, with even powers, we can pull out a secant squared and then use this to kind of make up everything that's left. Okay? So the question now is, well, what if there aren't even powers? What if there are odd powers? Well, now I'm going to use the substitution that u is secant, then du is secant times tangent. Okay, so now I'm going to peel one off of both. I'm going to have tangent to the sixth and secant to the eighth, and I'm going to have a secant tangent dx at the end. Okay, because I peeled a tangent and a secant away. Well, since I need my u to be secant, I'm going to change tangent to the sixth to be in terms of secant. So tangent to the sixth is the same as secant squared minus 1 cubed. We have secant squared minus 1 cubed. Okay, so now I use my substitution that I had up here. Okay, now I bring that down. So my integral becomes u squared minus 1 cubed times u to the eighth du. And I'd actually have to cube that out, be u to the sixth minus 3 u to the fourth minus 3u squared plus 1 all times u to the eighth. And again, I'd multiply that into every term, and then I'd do power rule. So the two methods here, if there are even powers, peel off a secant squared. If there are odd powers, peel off a tangent and a secant. Well, let's look at some other situations. Our last two situations we're going to look at, because the other ones, the mixing of powers, one even, one odd, we can adjust and work with, and they're very similar. But I want to talk about doing tangent by itself. If there is an odd power of tangent, you should rewrite tangent as sine to the fifth, cosine to the fifth, like that. which would rewrite, of course, as sine times cosine. And now use your Peel method to do this. Use the Peel method we did with sine. So Peel, rewrite it and peel off a sine or cosine. So if we peeled off a sine, we'd have sine to the fourth times cosine to the negative fifth times a sine x dx. So I've created a situation where cosine is going to be my u because, I need to put a d there, because my du is the sine. Of course, it's negative, so I'll have to adjust that. But then sine to the fourth I can rewrite as 1 minus cosine squared times cosine to the negative fifth, like that. Oops, I'm missing a term, sorry. So now, when I do my substitution that I designed, I get 1 minus u squared times u to the negative fifth du. And I can multiply this out, then multiply u to the negative fifth in, and then integrate with power rule. Now, an even power of tangent, I'm going to peel off one of the tangents, or I'm sorry, 1 squared. So I'm going to have it like this. Okay? So then I could rewrite this as the tangent to the fourth. Scoot this out of my way. Times secant squared minus 1. Okay? Multiply that in. I've got the integral tangent to the fourth secant squared minus the integral of tangent to the fourth. Now, this we can do now. We could make u tangent. Du would be secant squared. So the integral would be u to the fourth du. Boom, boom, boom. Easy enough. This one is back to being an even power. So what do we have to do? We have to repeat what we already did. We'd have to write it as tangent squared times tangent squared. Then we'd have to write it as tangent squared times secant squared minus 1. And we'd have to do that again. And we'd have to rewrite it until we got it down to a spot we could integrate it. Okay? So even powers of tangent are a little more work. We have to peel off a tangent squared and then kind of create a substitution. Odd powers we rewrite with sines and cosines. So in this video we looked at a lot of situations, and a lot of them are just kind of an introduction to you because they're not on the AP exam, but they are worth seeing as cool methods of using some substitution and some trig identities to do some pretty hard integration. So, the secants and tangents, if they're even powers, pull out a secant squared. If they're odd powers, pull out a secant and a tangent, and use those identities to help you. And again, the tangents, if they're both, if tangent's odd, rewrite it with sines and cosines. If it's even, separate it, pull out a tangent squared.